Our next panel is on PHMSA-funded research projects related to risk. Many of you may know that we have an active research program to improve pipeline safety. That's kind of the opposite end of the enforcement side of PHMSA. It's more of the carrot rather than a stick. And so we're going to talk about 3 new projects that have just been awarded related to risk. Our first speaker is Susan Rose, Principal Engineer with Kiefner A+ RTD.
Hi, I'm Susan Rose. I'm with Kiefner & Associates from Columbus, Ohio. And we're going to talk about our project, which is a study on risk tolerance criteria and its use in supporting decision-making. Okay. So it's important for pipeline operators to make risk-based decisions regarding the operation and maintenance of their pipelines. Many operators use some type of risk model already to help determine inspection intervals and prioritize maintenance schedules. Many also use the models to decide on additional preventive and mitigative measures. Regardless of the risk assessment approach, all pipeline companies must identify risks, prioritize them, and implement strategies to reduce the risk. But risk reduction comes at a cost, and setting and communicating risk criteria can be challenging. So defining risk tolerability criteria helps decision makers objectively evaluate risk reduction options based on the company's risk tolerance. The key is to determine the level of risk that is intolerable, where you want to reduce at any cost, and a level of risk that is tolerable, where nothing needs to be fixed. For risks that fall between the 2 levels, operators should work to lower the risks in areas where the benefits outweigh the costs. But how low is low enough? How much do you really want to spend? There are a number of approaches for defining risk criteria, and the degree of risk tolerance is expected to vary from company to company. Some are qualitative, semi-quantitative, or quantitative. And here's your typical risk matrix, which everybody's seen before. So the purpose of this project is to study risk tolerability practices currently used by pipeline companies, as well as other relevant industries, government agencies, and countries, to serve as a basis for comparison and guidance for use in the pipeline industry. Some examples of criteria can be human life, environmental damage, equipment, property damage, business loss, litigation loss, a bunch of other factors. And for natural gas pipelines, human life or life safety would be a driving factor, whereas a crude oil pipeline might be more impacted by environmental damages. So European regulatory bodies tend to define more quantitative risk criteria, while a number of other government agencies define more qualitative criteria using risk matrices or impact criteria based on the distance to the specified level of harm. And then there's different types of criteria as far as individual risk, which is quantitative, and it's based on fatalities from any given incident. It's set by comparing the risk associated with a specific activity to risk posed by other activities that individuals are exposed to, like driving a car, flying a plane, using electricity or gas. And here examples are like from the UK, where they're saying a fatality at more than once in 1,000 years is intolerable for workers who work at the facility and they're aware of the risks, down to 10 to the minus 7, which is negligible. And Brazil has criteria for industrial activities and for pipeline operations. And then there's societal risk, which is also quantitative, and it's the risk of multiple fatalities occurring from one single event. It's typically used to evaluate the risk of fixed facilities to the general public, where FN curves are broadly used, and many corporations have also adopted this method for internal evaluation of the relative risk of projects, plants, businesses, setting their own criteria. So here's an example of an FN curve for societal risk, where the top 3 lines are from the UK, and above each line is considered intolerable. So for the UK, the risk of an incident causing 50 fatalities or more is regarded as intolerable, and the frequency is estimated to be more than 1 in 5,000 per year. And if you look at Brazil, they drop the line at 1,000 fatalities. So if there's a potential for 1,000 fatalities, it's intolerable no matter what. And France just sets a limit at the frequency of 1 in 10 million years. So anything more than that is independent of the number of fatalities. Okay, so then there's also risk matrices, which can be quantitative, qualitative, semi-quantitative. We've all used them. Here's an example of a pipeline risk profile where the risk tolerance levels are based on a company's willingness to invest to avoid a certain event. These criteria are generally established by senior management and therefore represent the corporate risk aversion. It's the same thing, just showing that it can be used with index models based on relative risk scores, quantitative models that show the probability of failure, and also monetized models, which are based on the actual dollars that it would cost to bring the risk down to tolerable. Then there's also impact criteria, which is just based on consequence. It only considers like the distance resulting in a specified impact. The EPA uses this in their risk management plan rule, and PHMSA to a certain extent for their HCAs, where likelihood is not taken into account, it's just the consequences. Then there's pipeline-specific risk criteria. Brazil bases theirs on individual risk criteria. The Netherlands and the UK base theirs on societal risk for a given length of pipe. So our approach is just 3 tasks. We're first going to do a literature search. We're going to look at relevant industries and government agencies to see how risk acceptance criteria have been implemented and where maximum risk tolerance levels have been mandated. And then next, we're going to contact industry members, mainly pipeline operators, and try to determine what risk models they're using, if they've established risk criteria, what types of criteria are they using, how did they come about establishing the criteria, and are they using the criteria to look at P&M measures. and then we'll just issue a final report. So it's a 6-month project. We're also working with the MC Squared from Columbus, Ohio, and they're going to be supplying information. Like, their expertise is more in the aerospace nuclear industry, so they've been doing a lot of work with risk criteria for those industries. And then lastly, we have a technical advisory committee set up with representatives from Koch, Chevron, and PG&E. That's it.
Thank you so much, Susan. Thank you so much. We're going to hold off questions until the end of this panel. Our next speaker is Jason Scow, Manager, Integrity and Operations at CFR Technologies.
Thank you. So far, it looks like a very interesting discussion going on today. I'm very happy to be able to be a part of it with this presentation here. I'm going to be talking about a PHMSA research project. The title is A Critical Review of Candidate Pipeline Risk Models. And I'll be going over these 4 sections: the project objectives, background and incentive for this project, the project scope, and then I'm going to present a couple examples from risk models. Okay, to start with the project objectives, the objectives are to create guidelines for assessing and developing pipeline risk models that are based on the probabilistic quantitative approach. We've talked about several of the approaches here today. In this project, we're going to be focusing on this probabilistic quantitative approach. This is going to include a critical review of existing quantitative risk models, including models that are used in other industries, to determine whether there are some learnings from those industries that we can apply directly within the pipeline industry. When we develop the guidelines, there's going to be at least 2 levels of requirements, and the first one is listed there as standard requirements. This is to identify the minimum attributes required for a quantitative risk model, and also to define the risk measures that would be evaluated by the model. And I think there's been some good discussion on that already today, and so we hope to get further involved in that. The second bullet point, that it's titled Levels of Analysis, acknowledges some of the other discussion that we've also had today, which is regarding the complexity of some of the models. And so here the trade-off is the degree of analytical rigor and the data completeness that's necessary for the models to function properly. Okay, for background and incentive, firstly, something that we all know and we've been talking about is the risk models are used to rank pipe segments, to identify threats and guide integrity management decisions. Many current applications are based on qualitative models, and so I'm using the term qualitative here to refer to the index type systems that we've been talking about. These measure risk on a subjective scale, for example, on an index between 1 and 10. And on my next slide, I'll give an example of that and just point out some of the challenges associated with those approaches. They often involve having attributes and weighting factors. The weighting factors reflect the perceived relative importance. However, the results are subjective and often context specific. So here is an example of a qualitative risk matrix. This is a real matrix that is used in industry. It's used by the FAA, so not in the pipeline industry, but it is a real matrix. And some of the challenges are listed on the right there, one called rank reversal. What rank reversal means is that if you change the order of the categories on the top from ascending to descending, that you can potentially change the outcome of your risk assessment. Here they're listed as 5, 4, 3, 2, 1. If you change that to 1, 2, 3, 4, 5, you might get a different answer on the same assessment under the same conditions. Now, obviously, this is a logic inconsistency. It's not something we want in our risk models. Centering bias, the third bullet point there, refers to the fact that subject matter experts are less likely to choose the extreme categories. So 1 and 5 are chosen less often. And this may not coincide with either the severity or the likelihood of those options. So there is a bias towards not choosing those, which can cause some distortion in the outcome. Categorization errors refers to how we define those categories, the 1 to 5 that are listed there. They're often defined as an interval of some sort. For example, likelihood might be a probability. And if we redefine the size of those intervals, we can, again, change the outcome on a particular risk assessment. So these are some of the challenges associated with using this approach. They're not the only challenges, but the deceiving part of this approach is that it looks quite simple, but in fact the interpretation of the results is very difficult. One additional thing I'll point out is that you can have some places along this risk matrix that go directly from green to red if they go in a diagonal direction. So for example, D3 is listed as green. D3 is a major severity with extremely remote likelihood. And if we increase both the likelihood and the severity, in this case, we would go directly to red. And so we would change from a category that is classified as acceptable risk to unacceptable risk in one small move, which is counter to our intuition on how risk actually works. So these are some of the challenges. The probabilistic risk models address many of these limitations. The purpose of the risk model is to estimate the expected risk using objective parameters. I have some advantages listed here. Of course, there are also some disadvantages that I haven't listed, and those have been already talked about, such as the complexity and some of the data requirements. But here are some of the advantages. The results can be used in formal decision analysis, meaning that when we're comparing various decisions that we could make, we could get an estimate of how those decisions would impact the reliability of the pipeline. It links the uncertainty in the analysis to conservatism in the results. It uses objective data and engineering models. For example, it can use inline inspection data on measurement. It can use models for burst pressure or for the reaction of pipe under loads. It can be used to model rare events such as interacting threats, which I know is a difficult topic. In some cases, the interacting threats are very rare, and it would be difficult to model these using statistical data based on history, since they don't occur that often. The probabilistic risk models do allow for a methodology to help predict what those could be, although the challenges are still there. It also allows for the assessment of the value of new information. This is always a big question as to should we do another survey, or should we continue to do excavations or more excavations? Should we run another inline inspection tool? And there are many factors that can go into these decision-making processes, but some of the outputs of these risk models can help inform those decisions. This is the scope of our project. We're going to start with an industry survey. The industry survey is intended to determine the attributes that are favorable in a risk model. I've got some examples of attributes that I think will show up, but of course, the industry survey with operators and regulators will provide more information on that. That will be coupled with a review of the existing models that are available, including those in other industries, resulting in an assessment of the desirable attributes of a model related to these 4 points the results that come out of the model, the input requirements to the model performance itself, and some of the framework around how the model actually works. The result will be to produce guidance for quantitative model selection, for quantitative model development, and for the evaluation of risk. Now, we haven't done the survey yet, but based on previous experience, I would expect that some of these factors related to the successful application of a risk model would come up. And I think we've even talked about most of these already today. I'll just go over them quickly. The availability of data, the ease of implementation, basically the trade-off between the effort put into solving the model and the knowledge required to do so, compared to the value we get from the output. The flexibility to account for varying situations that operators face. Validation requirements, the consensus on a risk evaluation criteria, which has already been brought up. Acceptance by the regulator, fit within the integrity management framework, and incremental improvements over time, meaning that if we start with a simpler approach, can we move to a more holistic or quantitative approach over time? Or can we select the situations where it's necessary to do so and move to that approach over time? Here are some examples of levels of analysis that appear in the quantitative risk field. The first one is the subject matter expert opinion. There are methodologies that allow opinion-based information to be converted into what looks like a quantitative probability, almost like a probability distribution. And then the similar type of mathematics can be done on that as are done with quantitative measures. The second one is historical-based models. This looks at historical failure rates from databases and estimates a baseline failure rate based on that, which is then modified to reflect system-specific attributes. So for example, there might be a baseline failure rate for a particular pipeline that's exposed to a certain environment, but if the external coding is sound, it may be better than the average, so you would have a modifier to that attribute to reflect that the coding is better and that the risk is also lower. The last one is the reliability analysis method. This uses detailed engineering models that estimate the probability and consequences directly. Here are some examples of model attributes that we will be looking for. Safety, environmental, and cost-related consequence measures. I think the previous project will be very useful in that regard. A minimum list of threats necessary for a risk model. Failure modes and their effect on consequence. So failure modes would be how the pipeline fails. If it's by a small leak or by a rupture, you would have different consequences associated with that. And how does the model handle that? The link between mitigating activities and reliability estimates. So if we were to conduct what-if scenarios on different types of activities that could be done in the pipeline, how does that affect the outcome? And finally, risk results by threat and by location, which are necessary to know once the risk is evaluated, what do we do and where do we do it? So some of the basic attributes that I think that we will encounter, and there will be more as we go along. I have an example of uncertainty. I hope this is useful for the group as we talk about the probabilistic methods. I'm going to talk about probability of failure, which is only one side of the equation. There's probability and consequence. And a similar argument could be made for consequence, but in this example, I'm talking only about probability. In this example, we have a crack in a pipeline, and we have three parameters: depth, length, and wall thickness. And they're represented by these curves. And the reason they're represented by these curves is to express that we have some uncertainty as to the true measurement. Although we did measure this, there could be measurement error, and so we don't know the actual true value of the size of that crack, but we still want to do an assessment on it. In this particular case, we're going to take just one value, representative value, out of that, and let's say it's the 95th percentile for both depth and length. And so what we're trying to do here is take something that's quite deep and quite long out of what we think it could be and do the calculation that way. For wall thickness, we're just going to take the mean. So we can take these parameters and calculate the remaining life using fatigue analysis. So in this example, the burst occurs in 22 years. So we have a 22-year remaining life calculation based on these parameters. Now, if we go back to our input parameters and decide that potentially we could take a different wall thickness value, in this case I'm going to take the 5th percentile, so this is going to be a thin wall case, and we go back to our calculation, we can conduct a second calculation which is expressed by that red line. We can see now we have two answers for the same question that we originally posed. Now you can imagine with these input distributions that we could do this many times, more than just 2 times. So I've got an example here showing a shallow case. The feature is actually shallower than what we measured it to be. The result would be different again. Here's another case which is short. The defect is actually shorter than what we thought it was. And also this time it fails by small leak rather than burst. So we can conduct this experiment many times and draw this a little bit differently to make it look simpler with just dots on the graphic. In this case, we did 10,000 of these, and there are not quite 10,000 points on the chart, but I've only drawn this up to year 30, and many of these points would actually occur after year 30. There's many situations in which the remaining life could be quite long. If I zoom into the first 10 years and just look at the blue ones at the bottom, which are the leak, we can see that out of all those simulations that we did, none of them resulted in a failure until about year 5.5, which is that blue line there. Since we did 10,000 simulations, the probability is 1 out of 10,000. The second one occurs just after year 6, it's 2 out of 10,000, and then 3 out of 10,000, and then so on. So this is a very logical progression and quite straightforward, although there are complications in the overall process. It does require some Monte Carlo simulation. If we pull this back and look at the blue line, we can draw also a red line, which is for burst, so we have 2 parameters. And I'd just like to compare that with this green line here, which is the original calculation that we did, which indicates that in year 21 there's a 0% chance of a failure, but in year 22 there's a 100% chance. We know that this isn't right. This isn't what our intuition tells us about this approach, and so we apply safety factors and so on. The probabilistic approach takes a more direct application to incorporate the uncertainties in the measurements and in the input parameters, and provides us some insight which can help in the management of the pipeline. And I'll give you one quick example. Let's say we were able to purchase equipment that had a better measurement accuracy. If we were to apply that here, we would see a change in the output here that would help us decide whether it's actually worth doing that or not, and what some of the benefits would be of applying this better technology. In summary, the qualitative risk models are insufficient. The probabilistic risk models can appear more complicated than the deterministic models, but they do have some advantages associated with them. The guidelines will help to evaluate, select, and develop probabilistic quantitative risk models. And finally, the critical review will include existing risk models in both the pipeline and in other industries. Thank you for your time.
Thank you, Jason. Our next speaker is Ernest Lever, R&D Director of Infrastructure at the Gas Technology Institute.
Good morning, everybody. Our research project is a paper study on a review of approaches for preventing catastrophic events, and it encompasses a lot of what we've talked about today. The objective is a critical and structured review of approaches for preventing catastrophic events, both within and outside the natural gas industry. We're going to take a broad look at this and see what everyone's doing who addresses catastrophic events. We'll select the most appropriate approaches and models, identify the gaps that are in them, and develop a set of suggestions as to how to develop them further to suit our needs. In doing this, we will prepare the ground for the adoption and/or development of a suitable approach for the sector, and our ultimate goal is to issue guidelines for effective implementation in risk models and in integrity management programs. So catastrophic events are notoriously hard to predict and to prepare for because they are low probability, high impact events that do not behave well with standard probabilistic tools. They are rare and thus cannot properly inform a probability distribution function. There's a lot of difficulty if you look at how few of these events are, and if you do actually want to develop a probability distribution, it is not that easy to do. They are also unique, offering only limited learning opportunities from one such event to the next. Nothing fails because it's behaving in an average way. There are always very, very particular circumstances which are related to the specific application, a specific geography, a specific set of operating conditions. Hazard identification is an exercise that is problematic in the context of complex systems and emergent threats because hazards may be largely unknown. We think we know what the hazards are, but it's usually who would have thunk it when it fails. People didn't understand what the hazards actually were. Better catastrophe management plans combine risk analysis with resilience analysis. And resilience is one of those catchwords out there we really need to ask, what does it really mean? So resilience approaches require preparing for the unexpected, whereas risk analysis proceeds from the premise that hazards are identifiable. So several mature approaches seem to capture the essence of catastrophic risk fairly well, but sometimes they fail in properly propagating actionable results to any relevant supporting decision-making mechanism. Because to make decisions, it's all about context, it's all about uncertainty, and it's all about the impact of your proposed action on the rest of the system. What is its influence on the system as a whole? So we need all of that information to fully understand what set of decisions we should be making. So catastrophic events are typically low probability, high consequence events, as we've already said. And the associated engineering systems must confront dynamic and unpredictable environments, causing estimates of likelihood to be unreliable, if at all available. Even more difficult to forecast is the joint probability of the confluence of two or more major events, which is actually not rare when there is a catastrophe. We just have to look at what happened at Fukushima to see that these rare events do actually happen in conjunction, and then it gets really, really bad really, really fast. They have far greater combined impact or synergy than when they occur independently. Now, we have a poor understanding of how our failures propagate and are amplified within and across complex systems and systems of systems. It's important for us to realize that we are talking of interacting systems. At least two attributes of these complex engineering systems complicate the risk analysis. That's non-stationarity, that is path dependencies, changing boundary conditions, or interdependencies that generate different responses to identical stimuli that happen at different times. So what that means is that past record is not always a reliable predictor of future performance. We have to be very, very careful about this. A lot of these complex systems are very, very nonlinear. They don't behave the same way all the time. We have to take that into account. The second aspect is unexpected shocks, where an extreme or low frequency, high consequence events lead to the failure of the engineered system. It's a weakness of ours that we like to have these highly engineered systems where we think that we've taken into account everything that can happen, but we've usually forgotten something or we didn't realize something, and when that actually crops up, the entire engineered system collapses, and then we're in deep, deep trouble. So both of these issues can be resolved, at least to a certain extent, by various methods. And the goal of this project is to examine proposed and applied solutions to these and similar problems, which can ultimately be applied to the natural gas sector. A very important aspect here is the management culture and how it relates to systems of systems. And I just recently read a very interesting book by General Stanley McChrystal called Team of Teams, New Rules of Engagement for a Complex World. And in it he says, the pursuit of efficiency, getting the most with the least investment of energy, time, or money was once a laudable goal, but being effective in today's world is less a question of optimizing for a known and relatively stable set of variables than responsiveness to a constantly shifting environment. Adaptability, not efficiency, must become our central competency. Now, we've heard this actually being addressed in a roundabout way in a lot of people's questions and comments, where there's been a big drive by people to say, keep it simple, stupid. If I can't understand it in 30 seconds, it's probably a bad model, and I don't understand it, and let's see how we can change things. That's not necessarily the best approach, because we have this historic tendency, and McChrystal goes into this in his book, going all the way back to the Industrial Revolution, to try and categorize things, to become experts in one particular action, and to repeat it over and over and over and over again. But what that leads us to, it leads us to silos. We don't really understand how information propagates through the organization, or how failures propagate through a system. The charts which we have up here can represent either a human organization, or it can represent a set of risk models which are hierarchical. One risk model feeds up into another, and there's this assumption that there's this model or a person at the top who is a superstar, who understands everything, has taken every contingency into account, and just knows what's going to happen. It's very problematic, because in actuality, we've got tremendous feedback loops from one side of the system to the other, and they can lead to very, very unexpected events. And so this is what they were facing in Iraq when they were trying to deal with Al-Qaeda in Iraq, and they suddenly realized that they just had to completely change the way they thought about systems, human organizations, how transparent we are with information, and how we feed data from one person to the other, so that we always understand the context, we understand the uncertainties, and we understand the consequences of the action that we're about to take on the rest of the system. Because sometimes on one side of the system we think that we can be taking a very reasonable course of action, but it completely destabilizes another part of the organization. So that's something which we have to be very, very mindful about. So how do we adapt and prevent catastrophes? There are a few lines here. Each one of them looks very simple, but each one of them is at the top of a very deep series of discussions that we need to be having with ourselves. So we will review methods for modeling with thin evidence and proper weighting of thin evidence. We've already mentioned that these catastrophic events, there's not much to go on because they are so rare. So what people tend to do, they tend to look for models that we only have statistically significant factors, but this leads us to ignore a lot of what is actually contributing to the catastrophic event, and there's a problem with that. There's work in the literature which is showing that you're actually better off taking into account everything that you know, even if it isn't statistically significant, but feeding in the true uncertainties that you know and propagating these all the way through the system. So the trick here is not to choose certain values, but to actually do full probability distribution calculus, where you're feeding all of your probability distributions through all of the interactions and seeing how that comes about. It is also we also need to introduce causal reasoning into the models. When we have causal reasoning, we can make things a lot simpler than they seem. At GTI, we do a lot of work on elder piping systems as a vintage plastic piping system, and we've identified there 32 factors which we know interact, and that leads to 4 billion potential interactions that we need to take account of. But when we introduce causal reasoning and subject matter expertise, we can actually reduce that down to 49 flows of information through the system, which is a very tractable number. We can actually deal with 49 sets of interactions that we know we need to pay attention to. So that's where causal reasoning becomes very important. And when we go to hybrid causal networks, then we can actually feed in soft subject matter expertise, various other historic data together with well-known causal structures. And if we apply the rigor of Bayesian networks to that, we can make it all coherent. Coherence is very important because the probability of all of the system states which can occur need to add up to 1. And we already heard a little bit about that in the discussions about the problems with quantitative risk models or qualitative risk models, in that you can have a rank reversal and various things happening, because when people go and they set up these relativistic systems or they set a score from 1 to 5, you end up with lack of coherence somewhere along the line, and you can't compare anything to anything because you do not have a coherent system. So that's a very important aspect if you actually truly wanting to address catastrophic events. We can also identify precursor events, such as near misses, that may have good data. We have a lot of near misses that we all know about, and we all pat ourselves on the back and we say, well, nothing happened, we can carry on with business as usual. But quite often, these near misses are telling us a lot about what might actually go wrong with the system. If we pay attention to that, we might be able to go some ways to preventing actual catastrophic events in the future. We also have to figure out how to treat big data. Everyone says big data, but the question is, does it help or hinder decision making? You know, quite often big data can actually lead to more problems than help. There's also a tendency for people to look at the data, think it captures everything, and they do various statistical correlations on it which are fairly meaningless because they haven't actually gotten to what is the actual causality of how these systems of systems interact. Then we will also address the proper use of reasoning networks in the context of catastrophic events. Now that really is just how do we take these Bayesian networks, how do we do the proper probability calculus, and how do we feed it into the decision-making process. The next question which we'll address is, now, how do you pay for it all? Now, this is actually a very, very deep question because this gets into your risk tolerance and a lot of very, very tricky and difficult questions. So we'll review catastrophes in infrastructure over the past 15 years, looking specifically at lives, property, environment, new regulation, corporate image, a lot of the things which were mentioned by the Kiefner folks. They said they're going to look at a lot of these efforts. How do the total costs of potential catastrophic events get factored into the decision-making processes? Now, the elephant in the room here is a lot of people might be skirting around the value of a statistical life and feeding that into the calculations. Now, I've read recently that the DOT and the EPA have converged to a similar number for the value of a statistical life, about $9.2 or $9.4 million. And that's really how much we value our lives when we subject ourselves to the transportation system or various other threats, etc. But when we look at the true costs of something like a San Bruno event, there appears to be a multiplier of about 50 if we normalize it to lives lost as to what society is prepared to pay to not have their backyard turn into a fiery inferno. So we look at a catastrophic event very differently to normal risk, the kinds of things that the value of a statistical life applies to. So this is a very interesting question, and we have to begin addressing it, and we have to put something down on paper so that people can have meaningful discussion on this in the future. And that's the only way we can get to review potential business models for sharing the cost of developing adaptable systems for catastrophe prevention and mitigation. You know, I threw up McChrystal's slide there showing that this is complicated. There's a lot that we have to do. We have to change the way we organize. We have to change the way we think. We have to change the way we address these problems. All that costs money. Who's going to pay for it, and how do we share the costs? So we have to at least try to address that question. So in summary, I'll just repeat what we had in the beginning, because this is the structure of the project. We'll have a critical and structured review of approaches for preventing catastrophic events. We'll select the most appropriate approaches and models. We'll identify gaps, suggest how to develop them further, in order to prepare the ground for the adoption and/or development of a suitable approach for the sector. And the hope is that ultimately PHMSA and others will be able to issue guidelines for effective implementation in risk models and integrity management programs. Thank you.
Thank you so much. We will have a panel question and answer session before lunch, and microphone here and a floating microphone back there. You know, please state your name and organization and your question.
I think lots of subject. Adi Azam from IESS. I think this morning or in this session we covered a lot of stuff. Very hard to digest all of them and create lots of questions and comments, which I don't expect answered at this time. But there are 3 or 4 of them that comes to my mind. I just want to mention them. We talked about safety goals. Susan talked about that. But what wasn't addressed was the domain of influence. What is the population at risk? What is the environment and the cost at risk? So we need to know that. For example, in nuclear power plants, we talk about what is the radius of influence we are concerned about. You know, you should start thinking that way as well. I heard about modeling, PRM, risk modeling, very, very intriguing. I felt a couple of areas needs mentioning. I don't hear that many of you talking about some of the hazards that might be localized, such as seismic event, or external fire event, or nearby facility effect. I hope in your risk modeling those considerations comes to effect. The other item I noticed, and I am just making a point, please avoid falling in the trap of 95-95 in your uncertainty analysis. We are significantly wrestling with that issue. In the third presentation, my only comment is that if you want to drive something like Bayesian network, you are assuming you have lots of qualitative knowledge in order to create your network, your parent and daughter relationship, and conditional probabilities. Those are significant amount of data that either has to be driven by engineering models or actual operational data or subjective judgment. So that's quite complex causal model that you're speaking of. And our experience so far has been quite a bit difficulty with that area. Those are the comments I wanted to make.
If I could just address the final comment on the difficulty of using the causal network modeling. There's one aspect which we didn't touch on, and that is actually ontology-based systems and the whole approach of semantic programming. And what that actually allows us to do, that every time you come across something that wasn't addressed in your model, it is very, very easy to incorporate, and you don't have to adjust the entire model. You just merely add some more to your graphs, and you can incorporate new information. The other advantage of taking the Bayesian approach is that it also gives you a very robust way of dealing with thin evidence and developing your data on the fly, because you can start off with either uninformed or informed priors, which at least show you the sensitivity of the system to new information, which goes to the value of information, of new information, where you need to go and look for more information. And you also have a consistent, coherent way of updating your probability distributions as new data is generated. So that's something that we're acutely aware of, and we spend a lot of time discussing how do you actually deal with those complexities and dealing with aspects that you didn't initially realize were there, but later on come to light.
I would just like to add to the comment on the 95% confidence interval. I very much appreciate that comment as well. I think that's a very good comment. One of the sort of conclusions of the example that I gave that you can draw from that example is to be cautious of the 95% confidence interval, because if you take, for example, the 95th percentile of all the inputs, you don't necessarily get the 95th percentile on the output. The interactions of the inputs to the output are very complicated, which is one of the strengths of the quantitative approach. So I appreciate that comment.
This is Nathan Miller from DTE Energy. Quick question on the acceptability of risk. How would you do that for a relativistic model? It would seem like in a lot of cases you showed like 1 in 1,000 or 1 in 10,000. You're not going to get that with a relative model. Wouldn't you need to do a probabilistic model to come up with any kind of criteria for that?
Yeah, I think it's kind of,
Microphone.
oh, is it on? The only time I've ever done risk criteria is with the probability models, where what we did was have a facilitated like 2-3 day meeting where you've got all the decision makers at the meeting, and you go through a list of questions that ask the managers, how much are you willing to spend to avoid this event? I've never tried it for a relative. It seems like it would just be hit and miss, you know, just a gut feeling. But it worked really well with the meeting that we ran, having everybody there that had a good feel for how much things cost. And it's going to be different from company to company, of course. But eventually you come to a consensus at the end of the 2 or 3 day meeting where you have 2 levels.
I have a follow-up question on your comment there. It's very interesting, and that is that I'm wondering, and I haven't heard this morning yet, whether you've looked at the entire ALARP approach and the performance-based methodology for looking at those trade-offs, for doing a cost-benefit analysis and gathering the data to be able to determine your tolerances in a similar way to the way they do in offshore regulatory regimes in the North Sea, for example. It seems like they have a fairly well-established methodology for doing that, and I'm wondering to what degree that's part of your study.
We will look at that. I'm not familiar with it, but thanks for saying that, because I'll add it to our list. I'll definitely look into it.
I just have a simple question. What is, when can we expect to see these final reports for these 3 studies?
Yeah, we were asked that as well by Martin from Alyeska. At PHMSA, we fund a lot of research, and this is all on our public webpage. If you go to phmsa.dot.gov, we have a pipeline research database where we have quarterly reports and the final reports after the project is finished. So I believe the Kiefner report should be done in 6 months. So after that, there'll be a wrap-up meeting, and a PDF of the final report will be there, which you can download for free, as you know, this was funded with public money.
Good morning. I'm Steve Biagiotti with Structural Integrity Associates. I'm really intrigued by the GTI study because the path you're going to go down with aggregating the data and effectively mining it for the patterns makes a lot of sense. The nuclear power industry had the same issue in 2007 with a ton of buried pipe leaks. And they implemented something very similar to integrity management, but did it on a very compressed timeline of like 5 years. But part of their original, their regulations were to have everybody submit their inspection results to the aggregating body, in this case, EPRI. And we started mining that data. And actually, there's a new report I wanted to make you aware of that was published August of this year that is exclusively on the data mining results of the integrity of their buried pipe integrity programs. And one of the most interesting things that came out of that report was not that they were able to exactly pinpoint where to dig to find a problem, but because they were looking across a breadth of 50-something attributes, they were able to build statistical confidence on when these patterns occur, none of us found anything wrong. And that's equally as important as finding where to dig. So it's a report that was just put out. I was the principal researcher for that report, so thanks.
Thank you. Thank you for that information.
Okay, I think we'll, since we're on somewhat of a time crunch, we have a hard start back here at 1:30. I thought we'd wrap it up. And if there are other questions, feel free to submit them online or write them down, and we'll be sure to address them later. A couple of things I wanted to mention. First off, thanks to the panelists, for, this morning. Very much appreciated you taking the time to be here today. Susan Rose, Jason Scow, and Ernest Lever, thank you very much for your time. And then earlier, certainly, Jay Scrivener with Boardwalk Pipeline. And then from the regulator panel, Ian Calhoun from the NEB, Steve Allen from NAPSR, giving a NAPSR perspective. And then, of course, Steve Nanny and Ken Lee. So thanks very much to all the panelists. We will be back here again at 1:30. And let me just, I have one more important thing to mention that I should have mentioned this morning, but as you may know, today is September 9th, and this is actually the 5-year anniversary of the San Bruno pipeline failure. I know that had a huge impact on me, and I'm sure it's had a huge impact on many of you in the room. I think it's very fitting that we're having this workshop because I know I committed to, out of that, we will learn and we will apply those learnings. And to that end, we're here to learn. And I think this last panel is a great example of that. We're going to learn, we're going to get better, and that's what we're after because any accident is unacceptable. So to that end, I think it's a good day to move the safety ball forward. So thanks for all the input. Thanks for the great questions too. And again, for those of you here, there's a restaurant list out on the tables there, and we'll start promptly at 1:30. So thank you. Oh, I forgot.